Something is eating the sensors at the bottom of the Mariana Trench, and no one can explain why. In 2025, a JAMSTEC recovery team pulled up a seafloor monitoring unit from 10,700 meters down, and what they found made the entire room go quiet. The titanium housing was intact. The cable was not. Something had stripped it down to bare copper in clean, methodical bites, and whatever did it was still down there. The Mariana Trench is the deepest place on Earth, a black trench in the Pacific stretching nearly 11,000 meters straight down. Mount Everest could sink into it and still leave room at the top. The pressure at the bottom is over 1,000 times what you feel at sea level. The temperature hovers just above freezing, and there is no sunlight, not even a trace. Sound doesn't behave normally either. It travels farther and faster through that much water than it does through air, which means the trench hears things from thousands of kilometers away, long before anyone at the surface does. For decades, this is exactly why scientists trusted machines to do the work humans couldn't survive. No diver, no crew, just a sealed unit lowered on a line, left to record, then hauled back up months later. Send down a sensor, let it sit, bring it back, read the data. That system worked for 50 years, ever since the first benthic landers started reaching the Challenger Deep in the 1970s. Each lander typically carries a seismometer, a pressure gauge, and sometimes a hydrophone, all wired through a single external cable to a sealed instrument housing built to survive roughly 1,086 bars of pressure without flexing. That cable was always considered the weak point, just never for the reason anyone expected. Then it started failing in a way nobody had a clean answer for. It actually started small, and it wasn't even the first time. Back in January 1977, a Scripps Institution benthic lander was lowered into the western basin of the Challenger Deep at over 10,600 meters. 50 hours later, it came back up damaged, was repaired in a hurry, and sent down again. At the time, everyone chalked it up to the sheer brutality of the depth. 1,000 atmospheres of pressure crushing anything with the slightest flaw. Nobody thought to ask what else might have been involved. For decades, that explanation was good enough. Then, in early 2025, a JAMSTEC seafloor lander near the Challenger Deep stopped transmitting 11 days into a planned 90-day deployment. No storm, no tectonic event, just silence. When the recovery team brought it back up, the outer housing showed no major damage, but the external data cable had been reduced to frayed copper wire, the insulation gone in long, even sections, almost like something had peeled it on purpose. At first, engineers blamed corrosion. Salt water at that depth is brutal on exposed metal, and biofouling, the slow buildup of marine organisms on sensor housings, is a known headache for every observatory, from Japan's DONET network to the deep ACO hydrophone arrays. But corrosion doesn't strip insulation in clean strips. Corrosion pits and flakes. This looked deliberate. So the team turned to something with a real paper trail. In 2012, researchers studying Hirondelia gigas, the dominant scavenging amphipod of the Challenger Deep, found something nobody expected. This shrimp-like creature, barely 2 to 5 centimeters long, carries a unique cellulase enzyme, isolated and purified in laboratory tests, that breaks down wood and plant fiber into glucose and a sugar called cellobiose, fully active under the kind of pressure that would shut down ordinary biology. Earlier expeditions had already logged driftwood and coconut debris on Huddle seafloors thousands of meters down. Hirondelia had quietly evolved to eat what should never have reached it in the first place. That gave the engineers their first real lead. If something down there could digest buried wood for a living, using an enzyme system, unlike anything found in shallow water species, maybe it had simply found a new food source in synthetic cable insulation. Plastic-eating organisms are not science fiction either. Marine bacteria that slowly break down certain polymers have already been documented in laboratory settings. So JAMSTEC quietly revised its theory. Not a monster, a scavenger that adapted faster than anyone gave it credit for. For a while, that explanation held. Then the second lander came up, and this time the damage told a different story. This one had only been down for 19 days. The cable damage was worse, stripped in a tighter, more uniform pattern than the first, and this time the housing itself showed shallow scoring marks across the seal, the exact point where saltwater would get in fastest if the seal failed. Biofouling, the slow buildup of marine organisms on sensor housings, is a known headache for every observatory from Japan's DONET network to the deep ACO hydrophone arrays, and engineers know what ordinary fouling looks like. This wasn't that. An amphipod swarm chewing cable insulation for food made sense. An amphipod swarm targeting the precise weak point of a pressure housing did not. Marine biologists pointed out that amphipods don't coordinate like that. They're opportunistic scavengers, not engineers. They follow scent trails to food, not blueprints to vulnerabilities. So either this was an extraordinary coincidence, or whatever was down there had learned something about how these machines were built. JAMSTEC sent a third unit down in mid-2025. This one fitted with a low-light camera triggered by motion, the same kind of camera system that first caught Hirondelia on film back in 2009, swarming a baited trap by the hundreds. This time there was no bait. It logged 94 days without incident. Then, on the data pulled during retrieval, the final 11 hours showed repeated bursts of motion right at the cable junction. Dozens of small shapes converging and dispersing in the same tight rhythm, never lingering, never staying long enough for a clear image. The footage was grainy, the creatures barely silhouettes against the camera's own light, but the pattern repeated 9 separate times in 11 hours. Something was returning to the same spot again and again, like it knew exactly where to go. Independent reviewers who examined the footage said the movement pattern did not match typical amphipod swarming, which tends to be chaotic and food-driven. This looked closer to a foraging route, the kind of repeated, efficient pathway you would expect from animals that had already learned the cable was worth checking. And that is when the story crossed from biology into something stranger. A French hydroacoustic array nearly 600 kilometers from the original site, part of a network built to monitor underwater seismic activity, picked up a short repeating signal in the same frequency band researchers use to track tagged marine life. The timing lined up almost exactly with the third lander's failure window. No tagged animal was registered in that area on that date. No vessel claimed the signal. It was either a coincidence in a very large ocean, or something down there was being tracked by equipment nobody had deployed for that purpose. JAMSTEC has since redesigned its cable sheathing with a denser composite that early tests suggest amphipods can't process as easily, and 3 new units went down in late 2025, specifically to test whether the damage continues. 2 are still transmitting normally. The third stopped responding on day 41. No recovery mission has reached it yet, and the last data packet it sent showed the same motion signature at the exact same junction point as the lander before it. So, what's actually happening 11 kilometers down? The most reasonable answer is also the strangest one. A real scientifically documented organism that nobody believed could threaten human equipment has quietly figured out how to do exactly that, faster and more precisely with every deployment. Not a sea monster, not a hoax, just a 5-centimeter scavenger with the wrong enzyme at the wrong cable. Learning patterns that took us 50 years of failed sensors to even notice. But that explanation only holds if the behavior stays random. 3 for 3 on the exact same junction point isn't random anymore, and nobody at JAMSTEC has an answer for why. The next unit goes down in 3 weeks, reinforced and monitored around the clock. If the pattern holds, we will know within 100 days whether the trench adapted to us, or whether something down there has been adapting to us for a lot longer than anyone realized. If you think it's evolution or something stranger, subscribe for when we find out.